Hello everyone, welcome to my YouTube channel. So today I am going to discuss an interesting problem from group theory. This is an interview question and also the previous year question of TIFR and ISI. So the question is saying that let G be a finite group and H and K be two normal subgroups of G. Okay, not necessarily normal. We can take that H to be normal, okay, and H be a normal subgroup of G such that G mod H is isomorphic to K, where K is a subgroup of G, then G is isomorphic to H cross K. Okay, so there are many students who have a misconception that since G mod H is isomorphic to K, so it is kind of G divide H. Isomorphic means it's kind of same, so that will imply G is isomorphic to H cross K. But it is completely wrong. This is completely wrong. Okay, and you can make many counter example for this. So counter example, okay, counter example is like take G equal to S3. This is a non-abelian group, right? This is a non-abelian group, and take H equal to A3, which is identity, and these two 3 cycle. Okay, then G mod H has order 2 because order of G is 6 and order of H is 3, and H is clearly normal subgroup, so G mod H is order 2. That means G mod H is isomorphic to Z2, right? So G mod H is isomorphic to Z2, and you can take a subgroup of S3 which is isomorphic to Z2, like say identity comma this 2 cycle. You can take identity comma 1 3 this cycle also, this 2 cycle also. So that means G mod H is isomorphic to this, say this is K. Then if the statement is true, then G is isomorphic to H cross K, which is same as G is isomorphic to A3 cross this. Now A3 is a cyclic group of order 3 and this is also a cyclic group of order 2. That means it is cyclic group of order 6. That means this is isomorphic to Z6. That means G is isomorphic to Z6. But which is clearly wrong, right? Because G is isomorphic to S3, which is non-abelian. So G cannot be isomorphic to Z6. So that means here G mod H, here G mod H is isomorphic to K, but G is not isomorphic to H cross K. So very nice, right? You can construct many other example. Like you can take Z9 and you can take the subgroup to be isomorphic to Z3. Then Z9, like you take G is isomorphic to Z9, H is isomorphic to say Z3, then G mod H also isomorphic to Z3. But then this will imply G is isomorphic to Z3 cross Z3. But this is non-cyclic. This is non-cyclic, right? This is non-cyclic. But G is cyclic. Hence, this is a contradiction. So that's why you can make this type of many example. Now the question is that when it is true, like when we can say that if H is a normal subgroup of G, then G is isomorphic to H cross G mod H. Okay, if I take G mod H equal to isomorphic to K, then it becomes G is isomorphic to H cross K, right? So when we can say this holds, okay, so that's why the next question, and the next question is this: if G is a finite group such that H is a normal subgroup of G and there exists a homomorphism pi from G to H satisfying pi of H equal to H for all small h belongs to capital H, then this holds. So how do I prove it? Proof. Okay, so given that this is the homomorphism pi from G to H such that pi of H equal to H for all H belongs to capital H. That means pi fixes every element of H. Okay, and we need to show G is isomorphic to H cross G mod H, right? So let's define a map. We need to define an isomorphism. So let's define a map phi from G to H cross G mod H. Now, from the given condition, you have this map pi, right? So that means you need to use this phi map. You have to construct this phi map using the given pi map. So what is the obvious choice? The obvious choice is phi of G is defined as pi of G, which is an element of H, comma this left coset of H, G dot H, this left coset. Now we need to show that this is an isomorphism. So first of all, it is homomorphism, that is clear, because pi is also an homomorphism and this is an obvious map, the quotient map. So this is a homomorphism, which is clear. Okay, now we need to show 1 1. Okay, so let pi of G is trivial, and that means identity belongs to, say, H cross GH, say identity element of H cross GH, H cross G mod H, right? So then this will imply pi G comma GH equal to identity comma H, because identity element of G mod H is the H subgroup itself, and identity element of H, capital H, is the identity element of G. Okay, so GH equal to H, this will imply G belongs to H, and pi G equal to G, since G belongs to H and pi fixes the element of H. So that means pi G equal to identity implies G equal to identity, because pi G equal to G as well as pi G equal to identity, so G equal to identity. So hence phi G is identity, this will imply G is identity. So phi is 1 1. Now we need to show that phi is onto, right? We need to show phi is onto. Okay, phi is onto. So let x comma yh belongs to H cross G mod H. Okay, x comma yh belongs to H cross G mod H. Okay, so right, now we need to show that there exists G belongs to capital G such that phi of G equal to x comma yh. Right. So phi of G equal to pi G comma GH, which is equal to x comma YH, right? We need to find this. So small gh equal to YH, that will imply that Y inverse G belongs to H, right? That will imply Y inverse G belongs to H. Now how do I do that, right? So this part is very crucial, and this part is slightly non-trivial. Okay. So I am going to repeat again. So I need to show that phi is onto, right? I need to show that phi is onto. So that means if I take any element from the codomain group, I need to check that there exists an element belongs to domain such that phi of g equal to that. So I choose an element, say x comma yh belongs to h cross g mod h. So I need to show that there exists a g such that I need to show here I need to show there exists a g belongs to capital G such that phi of g equal to x comma yh, right? So if such an element we need to, if such an element exists, then what will happen? Then pi of g comma gh equal to x comma yh, right? So that means y inverse equal to, that means gh equal to yh, that means y inverse g belongs to capital H. That will imply y inverse g equal to small h prime, which is belongs to capital H. So that means g equal to small h prime y. So if I apply pi, pi is an homomorphism, so it will give pi of h prime dot pi of y. Now pi fixes every element of h, so that means it is h prime comma h prime dot pi of y. So hence h prime equal to pi of g times pi y inverse. Now pi of g is from the given condition this, right? Pi of g equal to x. So that means it is x dot pi y inverse. Then take g equal to x dot pi y dot, sorry, x dot, if you take g to be x dot y dot pi y inverse, then gh equal to yh, because y inverse g, I think I did some mistake. Let's, here it is. So see, there is some confusion of notation. Let's check it again. If small gh equal to yh, that means y inverse g belongs to h. That means, yeah, here is a mistake I did. Here it should be y h prime, right? Here it should be yh prime. So that means here it will be yh prime. So it is pi y dot pi h prime, which is equal to pi y dot h prime, and then h prime. So then h prime equal to pi y inverse times pi g, which is same as pi y inverse times x. This is h prime. Now take g equal to, say, y dot pi y inverse dot x. Then y inverse g equal to pi y inverse dot x, which is belongs to h. This will imply gh equal to yh. First part is done, and for second part I need to show that pi g equal to x. So pi g equal to pi y dot pi y of pi y inverse dot pi x, right? Now since pi y inverse belongs to H, that will imply pi of pi y inverse is same as pi y of inverse, right? Because pi fixes element of H. So we have pi of g equal to pi of y dot pi of y inverse dot pi x, which is same as pi x. Now since x belongs to H, so that means pi fixes element of H, so pi g equal to x. Hence the required g is this. This is our required g. Hence we can show that for x comma yh there exists a g. The g is this, such that phi of g equal to x comma yh. Hence this is onto. Hence this is an isomorphism.